Thank you so much. Yes, so my name is Ken Decker. I'm a senior aerodynamics engineer at SpaceWorks Enterprises, and I'm going to be going over how to run aerodynamic analysis with Cart3D Plus and OpenVSP. So for those of you who are unfamiliar with us, we're a company, a small business located in Atlanta, Georgia. We primarily work on engineering services and consulting for both government and private customers, as well as offer a number of commercial enterprise software platforms. Our kind of core competencies as a company are in launch vehicle and reentry system design, as well as high-speed aircraft analysis. And so, kind of over the years, as we've done this type of engineering work, we've developed a number of commercial software products that have kind of filled a gap in our engineering work, and we now offer the products that you see on this slide commercially. Today, we're going to talk about Cart3D, which is our commercial offering for CFD as a kind of a repurposed and extended version of the Cart3D distribution that's provided by NASA. So that's what we're going to go over today. So for those of you who are unfamiliar with Cart3D, Cart3D is an InVisid CFD software suite that was originally developed by NASA. It uses a fully automated volume mesh generation for analysis without the need for the user to provide a volume grid, and it leverages a number of state-of-the-art features like adjoint-based mesh refinement, gradient-based design and optimization, 6DoF simulation, and so on. Cart3D has been around for over a decade now. It has a very large user base across the aerospace community in the United States. It's available from NASA for U.S. contractors for U.S. government work. Where we kind of enter into the picture as SpaceWorks is we have come to an agreement with NASA to kind of offer a commercial distribution of that software so that people can use it for commercial uses and internal research and development. And as part of that, we've added some extensions to Cart3D that are relevant for this type of analysis as well that we've developed. So Cart3D Plus is how we're kind of is our name for the commercial distribution that contains all of the same Cart3D functionality that's distributed by NASA, plus some add-ons that we've developed to extend the capability. So those add-ons include our Scorch module, which is an add-on that's used to apply viscous and aerothermal corrections to Cart3D solutions, as well as an improved batch processor for improved scalability across things like large design sweeps, generating aerodynamic databases, and managing runs on high-performance computing. SpaceWorks is currently the only offer of the commercial license, but most of the kind of integration with OpenVSP that I'm talking about will kind of double for both the SpaceWorks commercial version and the NASA version. So we're trying to maintain backwards compatibility there as much as we can. And OpenVSP, since Cart3D has been around for a while, it contains a number of interfaces that can help automate the setup of Cart3D problems from OpenVSP geometry. So that's primarily what we're going to be going over today. So in general, OpenVSP to Cart3D integration kind of follows roughly a three-step process. So the first step would be setting up the OpenVSP model like you normally would. We've talked a lot today about kind of an overview of how you assemble geometries and define components, and then start doing some meshing as well. OpenVSP and Cart3D work really well together, particularly for conceptual and kind of preliminary level design. This is primarily due to the lower computational cost of the InVisid CFD solver versus some viscous solvers, and our kind of added on viscous corrections kind of maintains that low computational cost while building out the data set a bit. The requirement to run Cart3D is that you need a watertight triangular surface mesh of the vehicle outer mold line, or OML. And fortunately, OpenVSP natively supports the process of doing this triangulation and exporting a few different ways. So that we'll go over some of that later. And so once you have kind of the watertight surface mesh, then Cart3D kind of takes over and takes that surface mesh and generates a Cartesian volume grid about it, runs the InVisid flow solver, and then typically we would run with adaptive mesh refinement, or AMR, to have the refinement of the mesh be driven by the flow features. So it kind of takes some of the burden off of the analyst to have to mesh the volume grid to get resolution and where you need it. We kind of let the flow solver tell us where it needs resolution, and that kind of speeds up some of the engineering time associated with these runs. So just going over some kind of system requirements that you need in order to run all these things. So obviously you need an OpenVSP and a Cart3D installation. Either the NASA version or our commercial version will do for the flow solver. If you're using our commercial product, you'll need a license from us as well. Cart3D requires a machine that has a Linux operating system, so you can either run it on a Linux machine directly, or if you're using Windows, for example, you could also run it on a virtual box that has a Linux operating system, or on Windows subsystem for Linux, which is a pretty common way that we see people running it. The compute platform must have sufficient number of cores and RAM to run the flow solver. There's no hard requirement on what you need. It's really going to be driven by the size of the mesh and the time that you have to run your simulations. So a general rule of thumb that we carry around is about 7 GB of RAM per million cells. That'll kind of limit the maximum mesh that you can run on a given set of hardware. And then the time that it takes for the simulation to complete will be driven by how many cores you have, what your memory bandwidth is on your system, and things like that. So just kind of soft limits, just depending on your needs. If you're going to run our batch processor, you'll need a version of Python that's 3.8 or later. And then for full visualization capabilities, we would recommend using ParaView and TechPlot or some other visualization software that can handle 3D visualization of meshes. We do have some limited visualization capability built in using some external libraries, but you kind of get the full feature if you use one of those commercial platforms or ParaView for an open source option. So kind of getting into how do you do OpenVSP and Cart3D integration. So the first thing you do is you generate your vehicle OML like you normally would. The OML can be assembled from OpenVSP components, like we've kind of been discussing today. And each of these components might have some design parameters of interest. So to kind of get the full, I think, power of using OpenVSP and Cart3D, it's nice to kind of use this for design sweeps. So if you have variables that you want to trade, or if you have even like for a given design you wanted to look at different control surface deflections, for example, kind of setting up the model to be parametric allows you to kind of take advantage of some of those features. And we can even include fine geometric details such as small protuberances if those are relevant to your problem. Just keep in mind that the resolution of your volume grid will be driven by kind of the finest features that are going to be in your problem. So here I'm kind of showing some snapshots of the GUI that would go into a typical OpenVSP assembly. And the model I'm using here, I just downloaded from the OpenVSP Airshow site provided by Elias GH, and the link is down there if you wanted to download it yourself. And then there's also a wiki for some details of how to do the mesh generation. I'll kind of give the highlights here, but that's also a useful reference as well that I'll include it. So again, Cart3D Plus, it only requires the model of the wetted surfaces of the vehicle. So OpenVSP does have the ability to have internal geometries like structural layouts or fuel tanks or things like that. Those things can be omitted, or if they're included, you'll just have to make sure that your mesh doesn't contain any internal mesh elements. It's only going to be kind of a watertight enclosed mesh of the wetted surfaces. And then also a nice thing is that Cart3D also allows for breakouts of loads, both force moments and heating by component. So if you have particular regions of interest that you want to do isolated analyses on, if you assemble them in your OpenVSP model as isolated components, that component tagging will be preserved in Cart3D. So if you wanted to do, say, you wanted global forces and moments, but then you also wanted to do a targeted study on, say, control surface hinge moments to size an actuator or wing bending moments, you can extract those loads as well, as long as those things are defined as kind of their own components in your OpenVSP assembly. So next, once you have kind of an assembly that you're happy with and a set of design parameters that you want to analyze, you can adjust the wireframe to set the resolution. This can influence the surface mesh resolution depending on what approach you use to generate the mesh. Some use it directly, some don't. And it also can provide, better kind of CAD representation of regions, particularly with high curvature. So just kind of keep in mind that Cartesian Euler CFD does not require the same surface mesh resolution as a body-fitted viscous CFD, so it doesn't need to be as kind of finely detailed as some higher fidelity aero analyses, but really just enough kind of mesh detail to resolve features on the body that are of interest, like regions of high curvature, or corners, or those types of things. So once you have kind of the resolution that you're happy with, the next step is to export the surface mesh as a Cart3D tri file. Like I said, these things are directly supported by OpenVSP already, so I'm kind of showing an example of the export toolbar on the right there. The preferred export option is to use the .tri file, since that's what Cart3D uses directly. You can also use an STL file. Cart3D does have some utilities to do conversions between STLs and tri files that just add another step to the process. And one extra advantage of using the tri file is that it will preserve that component tagging. So if you did want to do those kind of isolated analyses on particular regions of the vehicle, you'd want to break those out. And so when you export the mesh, OpenVSP will dump the Cart3D tri file that Cart3D needs to run, as well as a .key file that basically just contains a text file that maps the integer tags that are in your mesh to the names that were defined in your OpenVSP assembly. So these are kind of just there so that you can interpret the results in Cart3D, mapping the IDs to the actual names that you define in your assembly. There's kind of three approaches to meshing in OpenVSP for Cart3D. The first one would be to export an intersected isotropic mesh using OpenVSP's CFD mesh interfaces. This is nice because isotropic meshes are good quality. And just keep in mind that the CFD mesh, there's options to export the surface mesh and the volume mesh. For Cart3D, you only need the surface mesh, which is nice. And this utility also has some options for fine-tuning the mesh, so things like defining sources and growth rates and things like that. If you want some kind of finer control over your surface mesh, has a lot of functionality that you can take advantage of there. Another option would be to export individual component meshes that are not exported. You can do this. You just have to ultimately make sure that before you run Cart3D, you have to intersect those meshes. Cart3D does have utilities that if you have unintersected meshes that you can intersect them prior to running the flow solver. Again, it adds another step, but there might be some advantages to doing that in some cases. And then finally, you can also intersect the vehicle mesh using OpenVSP's comp geom feature. That's the one that I tend to use the most. Just kind of, they find that to be kind of the most intuitive, but all three of these kind of have their own advantages and disadvantages depending on the nature of your problem. So once you get the surface mesh out, that is kind of the end of OpenVSP's job, and that's where we kind of pick up the integration with Cart3D. So we have to kind of configure our Cart3D input files to make sure that our inputs are consistent with what's going on in OpenVSP, and that primarily relates to the component tagging. So for those of you who are Cart3D users, you might know that there's several input files that Cart3D needs that concern setting up the flow solver, setting up the mesh, setting up the component tagging. For the legacy Cart3D, you can edit those XML files that match components and groups based on the tagging information that comes out of that OpenVSP export. We also have a kind of in our commercial distribution, an abstracted way of kind of combining those input files into a single YAML file and automating some of the generation of those large sets of input files. So that's another option to do it as well, basically using the YAML file to update with all of the component information and flight conditions and so on. And then for our commercial distribution, we also have a CSV file that we use to run large batches, potentially, of flight conditions. So it's basically just a table of mesh names, flight conditions, and if you have powered surfaces, you can even add propulsive boundary conditions as well. And so that kind of is there to make it easier to run kind of large sets of cases if you wanted to do design sweeps or error databases or things like that. So once you have your input files set up, next step is to run Cart3D. Again, our commercial distribution has a command line interface to kind of simplify some of the processes for executing and setting up the input files for each flight condition. Cart3D uses, or a common way of using it, I should say, is to run adaptive mesh refinement. So here's kind of an example of what that looks like. The flow solver begins by generating a bounding box around your geometry based on your settings, and then subdividing that bounding box in order to generate a coarse flow mesh. So on the left would be an example of a coarse initial mesh that has a very relatively small number of cells for a given flight condition. And the goal here is to basically run the flow solver on a coarse mesh, identify flow features of interest, and run an adjoint solver that then computes the sensitivity of a metric that you're interested in, like drag coefficient, for example, and identify regions of the flow domain that are contributing to sensitivity of that metric, and then provide resolution in those areas specifically. So in this case, we're running a Mach 3 example to illustrate the process. This is going to be heavily driven by the presence of shocks. So as the adaptive mesh refinement goes through, it's going to identify that the shocks are driving the metrics that we care about and provide resolution in that region. So the intermediate mesh, you can see we've increased the mesh from 43,000 to 278,000, starting to get some flow features coming into resolution here. And then by the end, for this case, I ran 6 cycles that ended up with a mesh of 6.4 million cells. And you can see we have really dense, resolution near the shock, and by this time we're starting to see forces and moments level off, and that's a kind of indicating that we've gotten probably about as good of a simulation as we're going to get for this case. And so this kind of takes the engineer out of the loop of meshing, and that combined with the low runtime of the Inviscid solver as compared to a viscous solver, kind of it makes this a very nice tool for kind of quick trades in the conceptual and preliminary phases at a kind of a manageable runtime. So once you get the flow solver, if you have our Scorch add-on, you can take the Cart3D solution and apply viscous corrections to it. Our Scorch module works by essentially taking the inviscid solution that comes out of Cart3D, running a stream tracer to identify regions of interest like stagnation points and attachment lines, and then mapping out streamlines and identifying running lengths on each point of the body based on the stagnation point or attachment line that a given point on the body sort of originated from based on the streamline path. And once we have that information, we identify engineering correlations for each sort of region of the body that we can then use to apply those viscous corrections. So this is done using boundary layer similarity solutions, kind of assuming that the Cart3D solution is a reasonable approximation of boundary layer edge properties and that the boundary layer is relatively thin so that the original geometry is a reasonable representation of the boundary layer edge geometry. And then we can use that to get skin friction corrections and use Reynolds analogy to get heating corrections from that. And so here's kind of an example of a skin friction and a equilibrium wall temperature distribution that you would get at the end of this analysis. And the thermal solver supports both fixed wall temperature analysis and radiative equilibrium analysis for those preliminary level thermal trades. So for post-processing, our Cart3D Plus package has some automated post-processing that's useful for kind of aggregating these large batch runs. So the first thing that we do at the top level is for a given batch, we aggregate the force and moment and thermal responses for each component of the body and for the full body and consolidate them into CSVs. For forces and moments, we break those out into pressure, viscous, and total contributions. And then we also include a convergence manager that outputs solver statistics for each run as well. So these will include things like if the flow solver failed and what error messages came up when it failed. It'll output statistics like the final mesh size if you're doing adaptive mesh refinement, and also the degree to convergence of whatever metrics it is that you're tracking. So this can allow the user to quickly screen large batches of cases to see, did some fail or did some not converge all the way? Maybe they need a couple extra cycles of adaptive mesh refinement. So it kind of makes that sort of process of wrangling these large database cases or large design sweeps a little bit easier. And then in addition to kind of the aggregating all of the top level metrics, we preserve all of the individual case post-processing statistics as well. So for each case, we'll output distribution files that you can use to analyze both the volume grid and the surface distributions in TechPlotter pair view ideally. And then we also include run files that contain histories of things like flow residuals or forces and moments. And then solver logs as well, so you can track individual solver messages, warnings, or errors for any particular case. So if you kind of use that top-level CSV to screen cases, you can then kind of probe each individual case to extract particular information or troubleshoot that way. We've done a number of validation exercises internally based on some of our internal programs and vehicles. Also at this last SciTech convention, we presented a paper where we benchmark the numerical performance and accuracy of these solvers. So I'm including a reference to that if you guys are interested in checking it out. Here's kind of an example of a calibration of our, or sorry, of a validation of our heat flux versus a RAN simulation for a launch vehicle taken along a slice down the center line. And here we can see that we're getting pretty reasonable agreement between a RAN solution and an Euler's plus Scorch solution. So the blue dots are kind of the Cart3D plus solution and the red are the RAN solution. And so this is going to be, close enough for a lot of conceptual and preliminary level exercises to kind of identify trends and support decision making. And again, we have more kind of benchmarking and accuracy reporting in the paper. And then kind of what you really get from a kind of a procedural perspective with this is really a significant speed up in the computational cost that you need in order to get that, kind of order of 10% accurate sort of solution as compared to a RAN solver. So we ran a cost benchmark compared to a viscous solver. In this case, we used Fun3D on a couple of simple benchmarks. And so we can see that the combination of the inviscid solver having fewer governing equations and a more efficient mesh storage algorithm leads to a kind of a lower computational cost per solver iteration. And then when you combine that with the fact that the inviscid CFD solver needs significantly fewer cells because it doesn't have to resolve viscous features like boundary layers, you end up getting, potentially a 5 to 10x speed up with individual solver iterations, and that can translate to a couple of orders of magnitude speed up when you talk about how much wall time it takes to run a case to convergence. So this is kind of why I think Cart3D plus OpenVSP makes it a really nice pairing for preliminary design, because you can kind of, especially with the viscous corrections, get the sort of same breadth of data that you would get from a RAND CFD, but at a fraction of the cost, and that enables significantly more design space exploration or sweeps that you can carry out. So just kind of some wrapping up remarks. At Spaceworks, we offer commercial license for the NASA-developed Cart3D software. The OpenVSP integration works for both. So if you're a NASA user, all of the kind of setup and handoff to OpenVSP is the same. We've extended the software suite into a package called Cart3D Plus that includes all of the existing NASA functionality, plus some improved capability for viscous and aerodynamic heating corrections and an automated batch processor. OpenVSP readily interfaces with Cart3D to allow for seamless transition to go from geometry to a fully featured aerodynamic and aerothermal analysis, and it offers an excellent cost balance between the low cost of Euler CFD, but the breadth of data that you would get from a RAND CFD, which makes it a very nice pairing for kind of preliminary and conceptual design activities. So if you guys are interested in hearing more information, feel free to reach out. But otherwise, I'm happy to take any questions if there are any in the chat.
Ken, thanks so much for giving us that overview. I'm sorry for shorting you on time up front. The YouTube stream is about 15 seconds behind, so we'll give them some time. If anybody has questions to open up in the chat, we'll get to those. I've been a huge fan of Cart3D for a very long time. We had tri-files in it before it was OpenVSP, so we've had tri-files pretty much all along as far as most people are concerned. And I actually think you're underselling the difference between Cart3D and, in that case, Fun3D, just because what you're not mentioning there is that every single one of those cases in Cart3D is getting rigorous mesh adaptation through the automatic mesh refinement. And so in a case where you've got, like we were showing, strong off-body bow shocks, at every angle of attack and every Mach number that you run that sweep at, you're going to resolve those, and you're going to have a very efficient mesh for that case. Whereas to get the same thing without any sort of adaptation, which is what I think you're comparing to, out of a traditional solver, you would need an extremely fine mesh to capture every possible off-body bow shock location, and it's just not practical. So, in addition to getting really great efficiency, you also get a rigorous mesh adapted resolve solution every single time for every Mach and every alpha. So that's really it's really a killer tool.
Yep, couldn't agree more. Thank you for that.
Still waiting to see if anything pops up here in the chat, so folks are still coming up. Appreciate the comments there, Rob, and I completely agree. Even going back to your welcome presentation about, the right tool for the right job to make the decision and move on, being able to use something like this to make quick decisions at a fidelity that makes sense for what it is you need to know about. Like, that is exactly the kind of stuff that we are talking about here. So really interesting stuff, and I'm excited to see OpenVSP and Cart3D still working so well together.
Yep, just a testament to that. I kind of have phases where I'm a regular OpenVSP user, and phases where I kind of don't touch it for a while. And so in preparation from this, I kind of, this is my first time probably in a year or so working with OpenVSP, and everything pretty much worked right out of the box. So, it didn't take me long at all to go from kind of that pre-made example from the air show to, getting Cart3D solutions for the presentation. So I think it's a really seamless integration that's pretty well maintained and very useful to kind of have in the toolkit for those types of analyses.